Hello, everyone, and welcome back for another NACE Calgary webinar. My name is Brett Johnson, and today I have the pleasure of welcoming Ron Ostafichuk from United Pacific Projects. So Ron is a leading software developer with over 23 years of experience in software design for the inline inspection industry, specializing in high-performance data visualization, mathematical algorithms, compression, and identification of features within ultrasonic and magnetic data sets. Ron is currently the Executive Director of Software and Applications at United Pacific Projects. Ron, thank you so much for joining me today. It's great to have you here.
Oh, thanks a lot for inviting me, Brett. I really appreciate it.
Awesome, Ron. So what are you going to talk to us about today?
Today, I'm going to discuss pinhole sizing and the challenges we face in doing that accurately, and show some of the results we've had, and let the industry understand better how we do it and how we can improve it in the future.
That's awesome, Ron. Well, I'm excited and looking forward to it. I think this will be a fantastic talk. So before we jump into that, I want to take a moment here to highlight some of our annual sponsors. Of course, our sponsors help provide this whole webinar series to all of our memberships here at no charge, as well as a lot of other things. But today I'd like the chance to honor one of our gold sponsors, Stantec. So Stantec believes that integrity begins with people. Their team of specialists have the technical and field experience to provide practical and creative solutions to ensure integrity of your assets. Their goal is to deliver safe, reliable, and regulatory compliant solutions to the oil and gas industry. Experts include inline inspection specialists, NACE accredited corrosion, cathodic protection, and coating professionals. They aim to work collaboratively to provide comprehensive integrity strategies for their clients. Integrity just isn't a job at Stantec, it's part of who they are. And of course, all of our other annual sponsors are a huge reason why we can do what we do. Our sponsors help fund several initiatives that NACE Calgary takes on to promote the knowledge of corrosion, sustainability, and asset integrity to our industry and the next generation of engineers. To each one of our sponsors, we thank you for your continued support. So to see the recording from our webinar and all of our past webinars, be sure to check out our website at nacecalgary.ca. And from there, you can find the YouTube channel link and then all the links to all our past webinars and everything like that. So Ron's going to give his presentation live. Be sure to stick around after his presentation as we'll move into a live Q&A session. Please submit your questions to Ron in your Zoom client by clicking the Q&A button on your screen. If you're joining us from YouTube Live, please enter your questions into the comments fields there, and then I'll also be sure to ask them. So without further ado, Rob, go ahead and share your screen and take it away.
Okay, well, oh, there we go. So a little about me. I've been in this I've been doing software for so many years I can't even count, but specifically 18 years in ILI, not 23. Sorry, Brad, I gave you some bad information before, because I took 5 years off to do SCADA because I'm a total masochist. Doing pump jacks was a very interesting time. Anyway, so, but I've had experience at Nowsco, BJ Baker, Desjardins, A+ RTD, Kiefner, OnStream. And in 2020, I joined United Pacific Projects. And so that's where I am now, and that's where this data is coming from. My presentation is all about the pinhole sizing, and and we'll have a QA after, as Brett said. The United Pacific Projects is a very new company. We have 15 staff, and we've been running commercially for a little over a year. We currently have a 4, 6, and 8-inch tool with magnetics and caliper, and 10 inches being tested, I believe, next month. We're just flying. So before I do my presentation, I'll do our little spiel. United Pacific was created to focus on the small diameter inline inspection market of Western Canada. We wanted to create products to push the envelope of data quality, accuracy, and ease of deployment currently offered to the inline inspection industry, while providing superior customer service and customized solutions. That's a quote from our CEO, Chris Meyer, by the way. So now that I've got the commercial stuff out of the way, let's get to the content. As many of you already know, MFL, or magnetic flux loss measurement, is an indirect measurement. It's like measuring the flow of water around a rock in a stream to determine the shape of the rock. The image on the top right is a colorized view of the axial, radial, and circumferential components. I'm just going to turn off my video because it's distracting me here. Sorry. These components represent the magnetic field for this 45% deep metal loss defect, which is shown below it here. The most important issue when measuring this flux is that the pipe has to be fully magnetized. Engineering is full of compromises, as you know, and we have a limited size and strength to the magnets in the tool. And this means we need to limit the speed of the tool to provide enough time to completely saturate the metal with the magnetic field. And one of the reasons we're very concerned about the line speed for the tool run is if the metal is not fully saturated, the signal swings when we hit defects is not as strong as what we have measured in our training data. And so we will tend to undersize defects, or for shallower defects, not even detect them. There's two methods commonly used to predict length, width, and depth of metal loss defects: equations and neural networks. The chart at the bottom left here shows the magnitude of signal swing for axial, radial, and circ sensors on the vertical axis, with the depth percent along the horizontal axis. There's an awful lot of points there. And you can see that a simple line equation like y equals mx plus b doesn't fit this data very well, because it diverges quite a bit as this field gets stronger. Neural networks are modeled on how biological neurons work. The simple models behave like a large statistical engine, really, that approximates relationships between the inputs and the output values, essentially like a large equation, but it's not really readable by a person. So on the bottom right, we have a diagram of how a typical neural network works. And we take a bunch of inputs and they get added up in each node. If the total value exceeds a certain trigger value, then the sum of that is sent to all the outputs. Actual neural nets will have many layers of these hidden nodes, they call them, to do these operations. And training of the network involves seeding all of these nodes with random values for the weights and trying to solve for the best results using a bunch of known input and output data we call training data. And I wanted to point out that neural networks are not a new thing. They've been in use in the ILI industry back since I was at BJ around the year 2000, I think, is when we started using random forest and neural networks. Random forest is another type of neural network. I won't go into the detail because this is a pretty good intro. So there's a lot of pros and cons to both methods. Equations are very challenging and time consuming to build, especially when there's a lot of inputs and the relationships between them are not very clear. The good thing about equations, though, is that when things go wrong, you can look at intermediate values in your calculations and try to determine where you've gone wrong and adjust it as appropriate. Neural networks are much easier to use in that they can handle a very large number of inputs with very little effort. This leaves more time to ensure you have accurate data being used for your training. They also tend to be more tolerant of variation in the parameters due to the way that the trigger system works that I described for the nodes. The bad thing about neural nets is that you can't debug them. You can only add or remove data and try it again and build a new model. Both methods, though, need to be tested against data that was not in the original training set to ensure that they're working as expected for new data. So there's pluses and minuses to both methods, but the neural nets are just definitely faster to work with. There's many instances of neural nets failing in real life. And the pineapple on the left and the fridge door full of ping pong balls is a great example of how sure a neural net can be for something that's completely wrong. So, the neural net is claiming 99% confidence on these two, and we laugh at it because we're people, but the neural net doesn't think it's funny. It's just numbers. The Tesla embedded into the truck is a real serious example of what happens when these networks fail. And pipelines are definitely more like the Tesla case than the pineapple case. However, problems that have a smaller number of possibilities are less prone to these errors. When you have a greater percentage of total possibilities used to train a neural network, like more dig data, the odds of a bad result will decrease. And luckily for us, metal loss in a pipeline is an example of a problem with a much more limited scope than images from a camera, which have a virtually infinite set of possibilities. This is an example of some of the parameters that are used in both equations and neural nets. On the left side, we have distance measurements, including things like the width of a valley and a peak at different signal amplitudes, and the distance between peaks in the data. So we've got distances between the tops of different peaks, and all of these can be used. But that's not all that can be used. There's actually quite a bit more in here that you can pull out of the data and apply for the distance information. The magnitude information on the right-hand side is typically from a valley or a peak to an average data value for the pipe, or the difference between the radial min and max peaks and the circumferential min and max peaks. But again, there's other parameters you can extract from this for your networks. And I want to point out, not all defects look like this. This is a typical defect. Axial slots, for example, don't have a clear signature that continues to the downstream. On the left-hand side, here's our axial, and it typically has a shape that resembles the defect to a degree. But on a really long axial slot, you'll see this disappear as it travels, as it goes downstream. That's one difficult challenge. Pinhole defects, on the other hand, are so small that they get caught between our sensors and our heads. And typically a sensor, the heads have multiple sensors on them. And if the pinhole is between two heads when you pass by, you have a larger distance between those sensors, which can reduce your confidence of sizing that pinhole correctly, because you're not going to catch the exact maximum radial swing and axial swings to feed into your calculations. Shallow defects are another case that have a very weak circumferential signal. And the circumferential is quite useful on deeper defects, but on shallow stuff, it can be almost just background noise. So there's many challenges to MFL measurement, and I won't cover them all here because we don't have all day. Now, specifically, sizing challenges for pinholes. Like I said earlier, they can be smaller than our sampling distance down the pipe. We typically sample at 2 millimeters. And the minimum sensor gap on our head is 4 millimeters. And that is the distance circumferentially around the pipe, is what I'm trying to explain. And between heads, you can have gaps from 7 to 17 millimeters. And that's a challenging region to measure. The largest pinhole in these examples is actually 3 millimeters in diameter, which is extremely tiny. The pinhole cluster on the left actually has two distinct pinholes, but they blend together and tend to look like a single deformation signal. An experienced analyst can see this strange shape at the bottom of the axial signal, but you can't really tell what it is. The pinhole group on the right has enough separation that you can see two distinct valleys in the axial data, here and here, but the radial doesn't barely show it at all. So there's a slight change in slope in the center, but you can't see it unless you're rotating the 3D view. And even then, you don't know what to make of it typically. I'm not showing the circumferential here because it looks just like a regular defect. There's nothing to see there. Tighter sampling distances, of course, you think would help, but they actually won't provide much value versus the cost. And this is because the large MFL signature for these defects blurs out around the defect and obscures the shape. And having more resolution isn't going to bring out more detail. I will show a pinhole example later that has a magnetic signal over 10 times larger than the actual defect dimensions in length and width to explain that further. So our approach to sizing has been to use neural networks to predict the length and the depth of a metal loss as accurately as possible, and then use that information to feed into our depth neural network as an extra hint, as well as many of the other parameters to try to improve our depth calls. And we've seen in my testing, I saw a really big improvement when I changed my technique to do this. And I want to be clear on this part though, because this means the length and width of detectable metal loss. So if a defect is roughly deeper than 3%, the magnetic signal starts to show. And that's the region that our neural nets have to focus on. And this can be a contentious issue sometimes because you can get a dig report from the field that has a metal loss that says it's 60% deep, 45 millimeters long, but the last 10 millimeters is so shallow, it's just included by the dig report people because it is definitely part of the corrosion, but the magnetic signal for it is virtually non-existent. So we're likely to see and report that as a 60 by 35 millimeter long defect, not a 45 millimeter long defect. And this is rare, it's not all the time, but it does affect the length training. So if you allow some of these features to go into your training data set without checking them carefully, you can be training your network wrong, and it can think that you'll end up getting bad lengths out of the neural net because you've lied to it. You basically said, hey, here's something that's 45, but everything about the data says it's 35. And so the neural net learns that it's 45. It learns the wrong thing. It's been lied to essentially. So we definitely don't want to put any pineapples into our training data. So next, I'm going to show you the results of our neural nets compared to our early equation-based calculations, because we started with equations when we first began this process, and we weren't happy with it, so we started to play with neural networks, and the results have been great. So this is our length unity plot. Two length unity plots for equations on the left, neural nets on the right. They show the predicted length on the vertical axis, plotted against the verified dig length on the horizontal axis. Ideally, this plot will show a perfect diagonal line that they'll match, but that's not possible when you don't have perfect measurements. So we use bands to show the defects within a plus minus tolerance. In this case, I'm using bands of 2 millimeters, which is the maximum distance the tool travels between each recorded scan of data. There's over 900 manufactured defects here and over 480 dig defects on this plot collected from over 130 commercial inspections that we've done. And we definitely push pipeline operators to do digs after running our tool to help us to improve our algorithms. And that's why we have a lot of dig defects so far. Our original length spec was 80% of the defects should be within 12.5 millimeters or a ½ inch of the actual. And the chart on the left uses our original equations from before we began running commercially and shows that if you add up the 48 and 31, around 79% is within 4 millimeters. So we're easily in spec there, even with equations. However, using the neural networks, the chart on the right shows that we're doing much better at 93% within a 2 millimeter length prediction. And I spent a lot of time trying to improve our equations and banging my head against the table and all sorts of things, but I could never do as good as the neural networks. And so I was quite astounded by this and happy because it's quite a bit better. In the end, we found our original length equations were really good on the manufactured defects, but it did poorly on smaller defects and pinholes in particular. You can see some artifacts here in the calculations on the equations, how it's rounding and it's got these weird white bands. Basically it was very limited in its predictions, and it wasn't able to do a good job. Whereas in our neural net, we're not rounding any of the length calculations down because through a bunch of testing, we found that those fractional lengths significantly contributed to the accuracy of the depth calculations later on. So we keep all that information until we report it, and then we round it down when we report it. Here we see the width unity plot, and it shows the predicted width on the left in the vertical axis plotted against the verified width on the horizontal axis. In this case, we use a 4 millimeter band on the plot to represent the minimum distance between sensors on the inner circumference of the pipe. The 2 millimeters for length, 4 millimeter for width were chosen so we could basically compare to our sampling distances in those two directions. The Nyquist theorem, which roughly states that you can't measure a frequency smaller than double your sample rate, applies here. But lucky for us, the magnetics for defects blur out much further than the physical dimensions. And so we can actually see defects much smaller than our sampling dimensions in the data. So our original width spec was the same as the length at 80%. Within 12.5 millimeters or a ½ inch of actual. The chart on the left, using our original equations, if you add up 59 and 27, that's like 87% within 8 millimeters, which is well in spec. But using the neural nets, we're at over 94% within 4 millimeters, which is just so much better. And our goal is just, if we want to make it better as much as possible. And a side benefit of improving predicted length and width is that the cluster interaction calculations and then your burst pressure severity calcs are going to be more accurate as well. When you have a better length, a better width, you know, it all trickles down to be better overall. Finally, we're at the depth plot. This is what everybody cares about the most, it seems, for our data. This is all of our data to date, not just pinholes. And I'll show the pinholes later, but I'm going to show how the length and width improve the predicted depth compared to using equations. On the right side, you can see the neural net is predicting 93% plus or minus 10% depth, which is really good. And that's why we just gave up on equations. We're like, the math guys win, we're going to use their neural nets. The left side shows the result of equations using all of our dig data to date, and is clearly not good enough for commercial use, as it's only 68% within plus minus 10% depth. And what we have found is that the depth calculation is very sensitive to this predicted width and length. And being inaccurate on length and width it cascades through the calculations and it makes the depth more spread out. I've tested this by introducing just length neural nets, just width neural nets, and seeing how it affects the depth. And every time, and using those different combinations, they definitely improve it each time. So I believe this is due to what the guys in the AI field like to call soft hints. And soft hints are kind of a cop-out in the neural net world, because they're basically saying that our neural net can't solve some things. A soft hint is an input that's fashioned in some way due to human expertise. And so by giving a length and a width, we know this is a length, we know this is a width, and we can quantify it and measure it and get the error bands down. We improve the depth calculation by feeding it these soft hints. I've tried going the other way and just firing all the inputs from the length and the width and the depth into a single neural network, and it doesn't do great. It's not as good as separating it out into the three. And this technique also has the added benefit that our senior analysis people are not locked out of the process. They have the ability to override the soft hints when things are too complex for the length or width neural networks. And that happens all the time because corrosion is bizarre. It's almost like random. It's almost like a lava lamp. There's always something that you don't have a sample, a test data point for. And so our analysts are able to modify that when needed. But luckily, most of the time, they don't need to do it. It does a really, really good job. But we're a new company with limited dig data, like 1,419 points is just the bare minimum I felt even confident showing to people. I would prefer a couple thousand, 3,000, 4,000. So we're expecting a few pineapples to pop up in the data yet, but hopefully not too many. And we're going to keep working on this. Okay, so now we're going to look specifically at the data for pinholes. The plot on the right, titled Pipeline Operators Forum, Metal Loss Definitions, shows the effective sizing capabilities of MFL tools. This plot suggests that pinholes are not sizable by MFL technology, as you can see in this bottom region where there's no highlighting. The charts on the left are our dig data filtered to show only pinholes in the 10 by 10 millimeter region, which this plot represents. And the trend on the plots shows a decent correlation to a diagonal line for both the length and the width, as well as detection down to 2 by 2 millimeters. Our data suggests that we can detect pinhole lengths and widths with reasonable accuracy of over 93% within plus or minus 4 millimeters. Some of the length data points here are a little wonky. That's a technical term if you don't understand it. But when I have time, I need to go back to some of these dig reports and triple check some of these outliers and try to figure out what is going on there. But in general, the width plot is as good as possible given a 4 millimeter minimum gap. But I actually have some ideas on how to try to improve that as well. And I'm going to be working on those in the near future. Now, here's what you really want to see with pinholes is the unity plot for depth. We have 170 pinholes here, and these are only from actual digs. No synthetic defects here, no manufactured defects. And you can see we're getting better than 90% of our calls within plus minus 10%, which we're really pleased with. We definitely want more data before we're going to provide an updated pinhole spec for our sales people to give out. But so far we've hit the ground running and we're very happy. Next, I want to show you an example of a simple pinhole to show you some of the difficulties we face. the defect on the top here is an 86 percenter that's 5 by 4 millimeters. The axial, radial, and circ signal response are below, and the defect strongly affects these three in the center, but this fourth sensor as well. So it's affecting a region 16 millimeters wide, and in the length direction, it's about 20 scans or 20 millimeters long, roughly. Our pig has a hybrid data collection mode, so sometimes it'll sample at a higher data rate depending on the speed it's running in the line, just to avoid any data loss due to slippage. So this red box is our call length and width, and the system called a 9 by 9 here. So it's right on the edge of our spec. The verified is 5 by 4, which is about a quarter of this box, which is about as big as my laser pointer there. But this is pretty reasonable given the size of this defect in the pipeline. Now I'm going to move on to a more complex set of pinholes. There's 2 deep pinholes here that are with a third one that kind of connects the two in this pattern. And the thing to notice is the MFL signature looks pretty much identical to a single pinhole in the previous slide. I'll just go back real quick. There's a single pinhole. There's 3 pinholes. Single, 3. Not much difference. This is an example of how physical geometry that we cannot see directly in the MFL signal is a huge challenge for us. But the neural network still came out and did a fantastic job. It even did better than for the single defect, calling it a 6 by 10 when it's a 5 by 7 defect. And the depth is within 6%. So yeah, we're a new company. We didn't expect to be able to do this good off the bat after a year of work. This is really good in my opinion and my experience, seeing this kind of accuracy out of our system. So the key factors in sizing, there's 4 key factors that we think are important. The first is tri-axial sensors. We need more data for detecting these difficult tiny features. I don't think it's possible to size a pinhole with a single sensor axis alone, just because it is so difficult. The second factor, testing of neural net parameters incrementally or by removal of parameter, helps us to arrive at better results much faster than fighting with equations. Third, calculating length and width completely separately from the depth and using them as hints for the depth neural network helps our accuracy while allowing our senior analysts to correct the system and handle any unusual cases. So we're not throwing our entire trust into an algorithm. Our fourth thing is training data integrity. It's crucial. This is the most important thing that I have found, and I've experimented a lot with this, so I'm going to rant a little here. This is so important that the CEO, Chris Meyer, and our senior analysts did all of the measurements for our original defects. An algorithm is only as good as the data used to train it. Accurate third-party dig results are critical. Garbage in means garbage out. This math is not magic. It's just a fancy equation. At the best case, a neural network can average out a small amount of garbage, but at the worst case, if you overtrain it, you're going to create a good match to your data, but it's going to have it's going to be very bad at dealing with new data. We have a relatively small data set, so it's really critical that we're very careful with all the data going into our test sets. If you overtrain the data, you're going to create many localized anomalies in the network that will pop up for different special cases and just bite you on your next inspection. So overtraining is bad. And on the other hand, if you reduce your training time, it can tell you how good your sample data is. So when I'm training a neural network, I can tell within 20 seconds of starting the training, I can tell if I've accidentally introduced some bad data, because I can see how fast the system is converging on a solution, and I can tell right away if things are going wrong. So I've seen people run training algorithms for days on supercomputers trying to force a network to give results, and it's just, oh, sorry, and it's just bad data. It's not worth doing that. It's a wrong approach. This problem is not that complex for a neural net. You want the neural net to find a simple general case, and that means less training, not more. Finally, I would like to say that actual complex defects provide valuable information we don't see in the manufactured or simulated defects, because people just can't dream up some of the bizarre shapes that we find in real pipe. In conclusion, oh, I thought I'd never get here. We believe this technique has greatly improved our sizing results for pinholes. But we firmly believe there's always room for improvement, and we want more dig results from the industry so we can work together to provide a better spec for the industry. We're hoping maybe late next year we'll be able to do something like that. Thank you very much for your time today. I hope it provided some useful information to you on how MFL sizing of pinholes and neural networks are done in the industry. And I am happy now to answer any questions. Thanks a lot, Brad.
Awesome. Thanks, Ron. That was, oh, do you still have more that you're looking to?
Oh, no, I just had the questions up.
Why is it sky blue, Ron?
I thought they were good stress relieving questions that weren't going to stress me out. So
well, there you go. That was an awesome presentation. It was a great, good overview of just the complexity of what it takes to try and size MFL features and some of the, you know, and some of the nuances about neural networks. You know, it's interesting because, you know, I remember when I was in university, I took a class on neural networks, and, you know, it didn't really make a lot of sense at the time. And in fact, you know, it was mostly a lot of math equations. And then we had to go through and, you know, we developed a little small neural network using these equations. And this thing was horrible at predictions, right? Like, you know, it would miss the predictions almost every time. But if you compared it to a set of randomly guessing a number, it was slightly better. So, you know, it kind of gave you some kind of hope. But it's interesting to see these days, you know, how much like neural networks are being more and more used. And so I think this is a really cool use case on that. So, I mean,
it's really fun to work in this field. Let me tell you, all these years and I still get a kick out of it. I really do.
I bet. Yeah, and it's only going to grow from here, right? Especially with you know, computers getting stronger and stronger and be able to handle larger sets of data and increased processing power. It's going to be fantastic. So, you know, one of the interesting theories about neural networks is, you know, the more, you know, is that the more you get good data within it, and, you know, as it grows more and more, you get this whole theory of, you know, large data being more related to actual truth on that. You know, so what do you believe, like, is that theory true? Do you think that when trying to size MFL features with here, that if you get more and more data, you're going to be able to perfectly predict the results?
I think statistically, yes, it's true. It's just practically impossible, because eventually you're going to have so much data that training the networks is going to take so much time that it's not going to pay off. There's a lot of variation in a single defect. If you pass the tool head directly over it, or slightly to the left, and then a little more to the left, and a little more to the left, and you could create a massive data set that in the end produced exactly the right result, but it would take an infinite amount of digs to do that. So
oh yeah, that's kind of it. Like if obviously may not be infinite, but it's a thinking of like, if you were able to get enough data, can you get to that perfect world where every defect, just using the sensors you have, could be perfectly estimated?
The real problem with that is that over time, the tool itself changes. So 10 years from now, you redesign the tool, the magnetic characteristics of that tool change, and then all your previous data is worthless for your new model. And so the march of progress kind of fights us and keeps us from ever reaching that kind of goal where we get a ton of data that's all perfect.
Mm-hmm.
Like in today's microchip shortage, people end up having to change chips. I've seen that many times in many companies where it's like, oh my gosh, this chip's not made anymore. They've got a new model. We have to change everything, and it has a slightly different signal response. Everything changes.
Oh, yeah. That's a really good point. And I guess that is why you'll be always forced to continuously evolve your tools, because you're just not going to be able to source the parts anymore. You need to build them the way they were.
Yeah. That's a real problem. So
no answers. So can you provide a little bit of your thoughts around how to just size and detect pinholes within general corrosion, or when you start to see like those weird complex anomalies like pits within pits, are those trained within neural networks? Is that something that you think that can be done?
yeah, actually, I was debating on whether to put that one general corrosion. I have a couple of cases in our last dig that were large general corrosion patches with a single pit in the dead center of it, and that's in our Unity plot. Like, we nailed it. So the neural net seems to be capable of doing a reasonable job at those general cases with pits in them. If I could remember where it is and pull it up on my system right now, I would show you the picture, but it is a big eye-shaped defect that is like 25% deep with a pit in the center that is over 45, and it's within spec for us. It does call it at a very wide, very long and very wide, but it got close to the maximum depth, like within our tolerances there, which it means that you're getting that severity right, which is a real critical thing for the industry, that it may actually be less missing metal than what you called, but the deepest part is still the deepest part. So yeah,
that's what every integrity engineer wants to know, right?
Yeah. Yep.
Awesome. Maybe a little context of how you got to the solution. So obviously there's, in this evolving world of, different models, machine learning models, different deep learning models or something. Why did you decide to go with a neural network?
Well, honestly, it was because I was frustrated as heck with the equations. I was tired of banging my head on the desk, and I'm like, I've got many years in this, and doing it with equations, I just could not get it tighter. I couldn't get the spec tighter, and I didn't like those numbers that I was seeing. Like, the length and width were coming into spec, but the depth was not, and that's so critical. So I decided, I did some research, looked it up, and then gave it a go, because normally in other places I've worked, I had math groups that would do that for me. Here, we're a small company, had to do it myself, and it was a little scary diving into that. But I did some online courses like you did at university. Udacity has a fantastic course, and I was able to dive in And I was surprised at how useful and simple it is once you get into it. And it's got a lot of potential for other, we've actually used it for a lot of other things here. And there's a lot of opportunity for some further presentations actually, because we've used it to help detect mill defects versus metal loss as well. And to actually give us an opinion on IDOD when you don't have a good IDOD sensor. So we've done some we just started throwing neural nets at everything, just it's like Homer and the makeup shotgun. I'm just shooting everything with it to see what comes out. and it's been fantastically fun and productive, which is just great. Like we're going to keep going down that road, and we will hopefully have some more presentations in the future for you guys.
Exciting. Maybe just going back there a bit of the context. So when you say that you're developing like just these normal set equations, like how do you do that? Do you use like in that old context on there, do you use machine learning on it? Is it regression analysis? Are you using physics? Like what walks into that process?
With the equations, basically it was looking at the known physics of the magnetic loss, which is the basics are that as the defect gets narrower, the same amplitude actually corresponds to a deeper defect. That's a common mathematical thing with the magnetic fields. And so I tried applying those type of rules and build equations to try to match that and come up with values. And I have friends in other companies that have had great success with that, and are quite confident in the results that they're doing with the equation-based stuff. But I was personally unable to do it. I guess I'm just not smart enough.
It sounds like you've got a good solution anyways
Yeah.
on that. So clearly smart enough for the neural networks.
Yes.
So one thing, Ron, you mentioned was you mentioned that the saturation of the pipe wall with magnetic flux is absolutely essential. So is there any way an MFL tool can measure or detect how much saturation there is on the pipe wall?
Yes, the axial signal actually has an average value, and you can look at that average value, and it should correspond to other known pipe wall thicknesses. So you can compare it to other runs and say, well, our axial strength seems to be weak in this case, or it looks like it's as high as it is for other cases. So we don't have any tools built in right now to do it, but that's a great idea. I should throw in our QA test. I should throw that in. I'm going to make a note and throw that in. We do a lot of statistical analysis during the QA part, and I come up with averages for the axial, radial, and circ, and standard deviations and all sorts of things, and we fire it in a database. But yeah, I should flag it.
Well, there you go. You'll have to send James Ferguson a big check for that idea, as that was his comment on there. So could you try to provide a little bit of an explanation for what dummies on neural nets mean on there? Is it based on statistical simulations, or is it something else? Or do you have any context about that?
On dummies, you said?
Dummies with neural nets.
Oh, dummies with neural nets. Oh, yes. Well, if you're using a neural net, first of all, I don't think you're a dummy, but you do need to understand the risks of overtraining and undertraining your data. There's a lot of mistakes you can make. And there's a lot of potential for mistakes that aren't your fault, but are due to the nature of the problem. So you have to understand both. You have to understand the physics of what you're putting into a neural net. You have to understand the potential ways this can fail as well. If you don't have a good grasp of that, then you are in danger of creating a solution that gives you lots of numbers that are wrong.
Oh, fair enough. No, I think that's some good context on that. So there must be some instances, where, your neural network goes and says that this depth is, X, but, the human will say that it's Y, like you were providing some examples from how your analysts will reanalyze. So how do you go back and reconcile those discrepancies? Do you use that to go back and retrain the model for the whole inline inspection, or what do you do with that?
No, we're limiting all of our training data to actual physical measurements. We don't introduce anything that is dubious in any way. So if I don't have a photo of that defect and with a ruler by it and a measurement, I'm not going to use it in our network, because there's too much risk that it's a bad point and it's going to send the results poorly in a direction for any defect near that shape. So, but our analysts, of course, they have a lot more experience looking at this stuff than the neural net, and they'll look at certain things and they'll be like, and they'll say that the prediction it gave me for that length and width are wrong. This is a complex defect. There's a couple of extra waves in the signal that the neural net didn't understand. And so it's usually not a big argument. It's the humans pretty much right 99% of the time. And we got to trust these very experienced analysts and their opinion and work with it and learn from it.
Totally fair. That's got to be a big struggle on that. And then I guess, even if you get kind of results later on, if an analyst you must have some method to track then if the result was an analyst driven result or a neural network result, because then you probably don't want to go back and take that dig result and well, you probably want to get your model to predict that, but not using how their method was done, right? Like what it was predicted.
Yeah, our analysts will look at these dig photos as well, and they'll learn from it as well if you get a really strange case, because they see things new regularly as well. That's a joke we make in the office. It's like, oh, great, something new. Great, I get to learn again by being wrong.
I think that's called the journey of life.
Yes. Yes.
Can you talk about some of your experience and findings with pinholes near girth welds? Obviously that's, pinholes are challenging enough, but near girth welds has got to be another level of complexity.
Yes, actually there's a lot to it, and there's so much to it that I kind of wanted to do another presentation on just that. The Unity plot that you're seeing there had actually some pinhole clusters right near a weld, within 30 millimeters of the actual bead of the weld. And we've developed some techniques, some filtering techniques for the weld region that allows us to size pinholes very close to the weld. I'm not going to say right up to the weld, because I have this fantastic case I want to show where there's one cluster 30 millimeters away. There's another cluster that's about 10 millimeters from the weld. And at that 10 millimeter point, it gets pretty close to impossible for us to size it. But it does show up in the data. But there's a bunch of techniques that I've developed for filtering that to bring it out to the analyst and show them, hey, there's something really bad on this weld. Yeah, if only I had an infinite amount of time, I could document all this stuff we found in a very short time, just from all these fantastic dig results that some of these companies have provided us.
No, that's awesome. So we're getting close on time here, so I just have time here for one more question. Thanks everybody for all the great questions that you've submitted. This has been another very lively and great Q&A session, so I appreciate kind of all the input in here. But last question on here, have you ever thought about how to use neural networks to like can the same theories of neural networks apply to being able to size detect cracks and crack-like defects as well?
Well, in my experience looking at MFL, and I've actually been part of a research project where we tried to detect cracks with MFL by ramping up the sensor density to like 1.5 millimeters between sensors and magnetizing to an extreme level. And we could not see cracks in MFL data at all. I honestly don't think it's possible. I'd love for somebody to prove me wrong. But that being said, some of the unusual things that you do see in the magnetic signature do indicate that we could try it. You know, that's what we've been doing. We've been doing this approach where we keep trying different neural nets on different problems, and like for the mill defects, and we could always try it, see if we see any correlation, because at this point, if you're not seeing it with the eye, sometimes the neural net can pick stuff out that you're not seeing, and sometimes it can't. And it really depends on the parameter choices that you make. But yeah, right now I don't think it's terribly likely.
That's fair. But do you think the data you can collect from ultrasonic sensors could be used in a neural network?
Yes, you can. I was also involved in the IWEX project at A+ RTD, where we were actually measuring cracks, though. And so I have a very good understanding of how microscopic cracks can be. And unless you're gonna be with regular ultrasonic, even with neural nets and everything else, I would doubt that you'd be able to call most cracks, even with ultrasonics, just because it is such an amazingly difficult problem. And it was a lot of fun working there, but on that project. But yeah, it's definitely difficult.
Fair enough. No, I appreciate that insight, and really appreciate your presentation today. I thought it was definitely great. Like I said, there was a lot of good questions coming in on here as well. So thanks, Ron. Thanks for your time going into this for sure. So with that, we're going to close off here. Thanks everybody for joining. Our next webinar is going to feature Monica Hernandez and Sandy Williamson, as they're going to go and present some of the findings from our Canadian NACE Impact Survey. So we're going to have that in a few weeks. So be sure to follow our LinkedIn page to get any updates on that when that webinar's registration goes live, and any other upcoming webinars that come in. So thank you again, everybody, for attending and all the great questions. Have a good weekend, everybody.
Thanks a lot.